Okay. Right. Okay. Good evening. We'll start. Can you first confirm whether I'm audible? Am I clearly audible? Audible, right? Okay. So today we are with day 9. Day 9 of S2 discussions. Day 9 means now we have done this thing for more than 2 months now, right? We have done this thing for more than 2 months now, and we'll continue to do so for the coming 20 weeks as well, right? So you got only 20 weeks and 2 days for the exam, right? If exam is happening on 10th of August as planned, we'll have only 20 weeks and 2 days for the exam, right? So that's a small time period, right? And time flies these days, right? Especially when we are busy with our things, always time flies, right? Time flies. Okay. So without any further ado, we'll get into the discussion. So I hope you have downloaded the questions from the channel. If not, I have pinned one comment in the chat, in the YouTube live chat. From there, you can download it, right? If you haven't downloaded it, right? And yeah, if not, you can navigate to the same link through WhatsApp channel, or if you are navigate into the Telegram channel, also you can find it there, right? So you can get it somewhere. Now, let's get into the discussion, right? I think, yeah, last day also we discussed viscosity. We started viscosity questions, and last day we discussed around 17 or 18 MCQs. And today also I'll be discussing around 17, 18 MCQs, and we are going to finish off all the questions, all the things in viscosity, right? And in the coming weeks, I'll be allocating expressions on friction, elasticity, thermal paths, right? And since 28 batch is also ongoing now, sometimes I'll be taking one S2 discussion on units and dimensions, right? Let's see, not sure, but sometimes I'll be taking, right? So those are things happening. Let's get into the discussion without further ado. Let me share the screen. Right, screen is visible. Right, let's start. All good, right? Let's start. 18. We are continuing from the point where we stopped last day. Right, 18. A small metal sphere of mass 40 grams is released from rest in a viscous medium. When the velocity of the sphere is 0.03 ms minus 1, the viscous force on sphere is found to be 0.1 newtons. If the buoyancy force is negligible, the terminal velocity of the sphere is... Okay. Now, one data is given. Using that, we can find something like this. See, one data is given. So we know for spheres, Stokes equation is valid. F equals 6phi eta RV. Right? Now, if I apply these given values, 0.1 equals 6phi, eta is not given. Eta is not given. Mass is given. Velocity is given. Even R is not given. Right? Then velocity is 0.03. Right, from here, we can find something for 6phi eta r. We can find something for 6phi eta r. See, if we subject 6phi eta r, 6phi eta r is 0.1 or 0.03. No? 0.1 or 0.03. So as a value, that is 10 over 3, right? That is 10 over 3. So let's keep it there. And then we need to find the terminal velocity. We know terminal velocity is a uniform velocity, right? Then mgx, we are asked to neglect buoyancy. So we'll be neglecting the buoyancy force. Then at the terminal velocity, at terminal velocity, we say Vt, acceleration equals 0. Since acceleration equals 0, F equals mg. Since acceleration equals 0, F equals mg. F equals mg. Right? Then F can be expanded again as 6 phi eta r Vt, terminal velocity, equals mg. Right? For 6 phi eta r, I have something here, no? For this part, right? For this part, for 6 phi eta r, we have an answer here, that is 10 over 3. 10 over 3. And Vt is Vt. Mg, 40 grams. M is given 40 grams, then which means we know mg. Then 40, convert this to kilograms over 1000 into g, 10. Right. Simplify this. Simplify this. Then 0 to 0 cancels. This 0 to 0 cancels. Right. Then subject Vt from this. Vt equals 4 times 3 is 12. 12. 10 to the minus 2. Right? Yeah, it's there. That is 0.12 ms minus 1. 0.12, it's 3. 0.12, it's 3. Right? A different data was given. Then using that, I found the value for 6 phi eta r. And in the calculation of terminal velocity, we can use that same value when we need it. Right? Next. A small sphere falls through 2 columns of immiscible liquids in a deep container as shown in the figure. Right? If eta 1 and eta 2 are the viscosities of the two liquids and V1 and V2 are the corresponding terminal velocities of the sphere respectively, then, okay, so we know terminal velocity of a sphere is given by this equation. Terminal velocity is given by 2r squared g rho object minus rho liquid over 9 meter. No? This is the equation, right? Now let's cut off the constants. Let's cut off the constants. Same radius, then radius is constant, 2 is constant, g is constant, right? And 9 is a constant. 9 is a constant. Yeah, the rest remains. 9 is a constant, the rest remains. Then this is what we get. Terminal velocity into eta, Vt eta. Okay. Terminal velocity into eta, Vt eta is proportional to, not equal to, 1 second. It's proportional to rho O minus rho L. Rho minus rho L. Right. Now, we can apply this for these two liquids. Now, we can decide this just by looking at the way they are, right? If this is rho 2 and if this is rho 1, we know this density is greater than rho 1 because there is a liquid which is below the what we have this container. In the container, right? The liquid below the container. Below means there is a higher density. That's a higher density. Then rho 2 is greater. When rho 2 is greater, see what happens. When rho 2 increases, see, when rho 2 increases, this term decreases. When rho 2 increases, this term decreases. Which means, if you apply this for these two, for first one it is eta 1 V1, right? Proportional to rho O minus rho 1. And for second one, that is eta 2 V2, proportional to rho O minus rho 2. Rho 2 is greater. Since rho 2 is greater, this value is lesser. Since rho 2 is greater, this bracket is less. Bracket is less means this value is less. Right? So therefore, eta 1 V1 is greater than eta 2 V2. Eta 1 V1 is greater than eta 2 V2. It's 4. Right? See how that logic was used. Eta 1 V1, sorry, eta 1 V1, it's 2, ne? It's 2. Eta 1 V1 is greater than eta 2 V2. Right? Likewise, simple logics. Simple logics. 20. how much more thumb pressure should a nurse apply in administering an injection with a needle of inside diameter 0.2 millimeters compared to a needle of inside diameter 0.4 millimeters. Right. Now, even though diameters are given, you can find the radii. This is 0.1 millimeters and this radii is 0.2 millimeters radii. Assume that two needles have the same length and the volume flow rate in the same is the same both rate is the same in both cases. Okay, right. Now, if there is about a tube, we have only one option, that is Poisson's equation. So apply Poisson's equation. What is Poisson's equation? V over T equals pi delta V R to the power 4 over 8 T del. Right. Then here also you can cut off the constants before getting to the question. Phi is a constant, right? And pressure is asked, right? How much thumb pressure? Yeah, pressure is asked. Radius is different. Eta, 8, L, everything are same. And about V over T, assume that two needles have the same length and same volume flow rates. This is also same. Now, this is the only thing remains. See how is it? Delta P is inverse proportional to R to the power 4. Apply this for these two scenarios. Apply this for these two scenarios. Then in the first case, delta P1, let's say, proportional to 0.1. 0.1, right? It is 1 to the power 4, no? Right? Because 10 to the power is going to cancel off. And in the next one, delta P2, that is 2 to the power 4. Divide these two. Divide these two. Then delta P1 over delta P2 is 2 to the power 4 is 16. 16. So that is 16 times. Right? 16 times. Poisson's equation. Poisson's equation. Right? 21. 21 is a kind of a good question. A lead ball of radius A is fixed from a toy gap in water in a large swimming pool as shown in the figure. The densities of water and lead, rho W and rho PB respectively, and the viscosity of water is eta. If x and y components of velocity of the ball at a certain instant are Vx and Vy, right? It's given here. So this component is Vx and this component is Vy. They are given respectively. Then the magnitudes of the corresponding acceleration components at the instant would be, right? Acceleration components. First, let's find the horizontal one. Now, if you think of this ball, if velocities are, two velocities are given, horizontally and vertically, then accordingly we have to mark the viscous force, right? When it is moving to the right horizontally, viscous force to the right, say Fx, is acting backwards, and when it is moving downwards, viscous force to the upward direction acts, say that is Fy, and other than that, in upward direction, upthrust also there, upthrust is also there. Right. Now, first, if we consider the horizontal motion, right? Horizontal motion, let's apply F equals ma in this direction. That's the only option. We have to find an acceleration. No? Apply F equals ma in rightward direction. Right? F is Fx. Right? F is minus Fx actually. Minus Fx. Right? And M A. Right? F is minus 6.5 because that is not an acceleration, that is actually deceleration. That's why it comes along with the minus sign. 6.5 eta R is given as A, sorry. 6.5 eta A V X equals M can be written as 0. M can be written as 0. Right? So we know M equals 0. V is 4 over 3 pi A cube. Rho is rho PB. Right? V rho A. Right? Now, since acceleration and radius is same, let me write this as AX, horizontal acceleration, AX. Right? Simplify this and see. 2 times 2, 2 times 3. Right? And this A2, 1A cancels, A squared remains, 5 to 5 cancels. Subject AX from here, subject AX. Then comes to minus 9 eta Vx over 9 eta Vx over A squared, 2A squared, right? 2A squared rho PB, 2A squared rho PB, 9 eta Vx, 2A squared rho PB. We have that in answer 1 and that in answer 3 and in 4 also. Now we got 3 answers having the same. And then the vertical acceleration. To find vertical acceleration, apply F equals ma vertically, right? Then vertically downwards, F equals ma, right? Then that is vertical downwards. We have mg as well. Mg minus u minus fy equals may, right? Simplify and see. Mg minus u is v rho g, right? V rho water, it should be rho water g minus f is 6 phi eta rvy equals may, right? Plug these values and simplify. M is v rho. V is same as before, 4 over 3 phi a cube, right? Rho PB, rho object, right? G minus V here is again same. Shall I take it out? That would be easy, no? V is common for both of them, then we'll take it out. And here, from here only, rho WG remains, right? Then here only rho WG remains minus 6 phi eta RVy, and M here is 0 again, right? 0 again, 4 over 3 phi see, 4 over 3 phi a cube, rho PB again, rho PB a y, right? It's a simplification. We can divide the entire thing by this term. See, at once I'm going to divide this entire thing by this term, 4 phi a cube rho b. We are going to divide this entire thing by this term, right? At once. Then this whole thing cancels. This thing here cancels, no? Right? This thing here cancels. Then what remains there is, look at here, rho PB minus rho W G. No, by rho PB also it's dividing. Wait. Then by rho PB also it divides, which means only one remains here. By this whole term it divides, then G is out, then 1 remains, 1 minus rho W over rho PB, right? Minus, when this is simplified, 9 eta V y over 2a squared rho PB, right? So it's in answer 1. And in the given answers, there is a small typo here. These values should be corrected as Vy, yeah, like that. So it's 1. That's a good question came. Right? A different idea, because now usually we have only one velocity when we are dealing with spheres, but here two velocities are given. When two velocities are given, we have to think a little bit out of the box, and you have to mark the Stokes, use the Stokes equation and mark the viscous force in two perpendicular directions according to the velocities given, right? That was the thing. That was the difference. 22. As shown in the figure, a box is placed on an oil layer of viscosity E and thickness D. The area of surface of the box in contact with oil is A. What should be the other contact applied on the box in order to move it at a constant velocity eta, right? Then let's say this is the viscous force here, F dash, right? So we know in order to move in constant velocity, there is moving in a constant velocity, that's a force equilibrium, no? Then what happens is F dash equals F. Then we can expand F dash using Newton's equation, eta A delta V over D equals F, right? Then eta A is given delta V, difference in velocity. Now, if this is moving with velocity V, first layer of the liquid dash V, and since this surface is at rest, last layer of the liquid has no velocity. So it is V minus 0 over D equals F, subject F. F is given by eta A V over D, eta A V over D, eta A V over D, it's 2. It's an easy one. Eta A V over D. Right? 23. Figure shows a section of a long horizontal rectangular tube of height 0.016 meters, having a large surface area and filled with a lubricating oil of viscosity 0.072. What is the force F required to drag a very thin plate P of area 0.4 square meters with a velocity of 0.02 ms minus 1 along the middle plane between the top and bottom surfaces of the tube as shown in the figure? Right. Now, if we think of a plate, listen, this is a good point about a plate. Plate is in contact with the top surface. Plate is in contact with the top surface of the liquid. Right? Because of that, there is a viscous force acts on the top surface, and it is in contact. It is in contact with the liquid from the bottom surface. So there is another viscous force which acts at the bottom of the plate. So when you deal with plates, since there are two surfaces which are in contact with the liquid, two forces are acting. Right? So I'll find one force here. F equals Newton's equation, eta A delta V over D. Apply and simplify. Eta 0.072. So it can be written as 72 times 10 to the power minus 3. No? Right? Times area. Area is 2 times 10 to the power minus 2. Sorry, 0.4. Area is 0.4. Area is 0.4, which means 4 times 10 to the power minus 1. Right? And delta V 2 times 10 to the power minus 2 minus 0 over D. If total gap is 0.016, right, this should be 8 times 10 to the power minus 3, half of that value. 8 times 10 to the power minus 3. Simplify this and find 1F. Find the value of 1F. Right? Then this is 2 times 4. Then 4 to 4 cancels. 4 to 4 cancels. Right? Then only 72 remains. Okay. Then F equals, simplify these 10 to the power 3 to minus 3 also cancels. Then minus 1 minus 3. Then that is 7.2 times 10 to the power minus 2. No? This is only 1F. 1F. Then the opposite force which should be applied here is, right? So if this is F dash, to drag this, F dash should be 2F at least. 2F. Then 2 times this value is 14.4. No? 14.4. 72 times 7.2 times 2 is 14.4 times 10 to the power minus 2. That is equivalent to 1.44 times 10 to the power minus 1. Right? So it's 5. That's a good one. So in plates, that's happening always. Right? Viscous forces are acting at either sides. Viscous forces are acting at either sides. Right? It happens in plates. Next. Okay, 7 identical spheres, each of radius r and mass m, are packed inside a hollow spherical container of mass 20 m and radius 3 r. When a container is released from the water surface of a calm deep sea, it moves vertically downwards to the bottom of the sea. Once the container has reached the terminal velocity V0, it's opened and metal spheres are allowed to continue their motion vertically and independently towards the bottom of the sea without any influence from the container. The variation of velocity of metal sphere with time is best represented by. Okay, initial scenario is, in initial scenario, there are 7 balls inside. 7 balls inside, right? Each mass m and this mass is 20 m. So altogether mass of this entire thing is 27 mg. 27 mg, right? So let's say upthrust is U1 and viscous force is F1 here, right? We can get an idea about its terminal velocity by applying an equation here. Then at terminal velocity, we can say U1 plus F1 equals 27 mg. U1 plus F1 equals 27 mg, right? Then U1 plus F1 is 65 eta. This is 3R, no? 3R V naught equals 27 mg. Something like this, right? Then if you think of a small sphere, this is how a small sphere is, radius r and mass mg, and it has upthrust. Now radius reduces by, we can write this at once, radius is decreased by 3 times. When radius decreased by 3 times, volume decreased by the cube of that value, then what's the value? 27 times. 27 times. It decreases by 27 times. Then for our is, let's do this way. What if I use this as u and this as 27 u? That is easy, no? 27 u. Then this is 27 u. This is 27 u. 27 u. Right? Now, since 27 is common, it will be easy if we subject this. See? 65 eta 3R V naught equals 27 is common here, take it out. Then mg minus u. Something like this. Something like this comes. And for the small one, right? U and F, let's say. For the small one, U plus F equals mg, right? Then U plus F equals mg. F is 65 eta R V now equals mg minus u, right? Mg minus u is created. Then we can plug that here for mg minus u, right? Then for this mg minus u, you can plug 65 eta RV. See what is happening. 65 eta RV. Then at the very moment you plug it, 65 eta R cancels. 65 eta R cancels. Then 3V naught equals, see, an answer is coming now. Let me write it here. Then 3V naught equals 27V. 27V. Simplify, then V equals V naught over 9. We found the new velocity, new terminal velocity as V naught over 9. We found the new terminal velocity as V naught over 9. Then terminal velocity is decreasing from V naught to V naught over 9. Decreasing from V naught to V naught over 9. Then in the first graph we have V naught over 9. In this one we have, it is not a decrease, so it cannot be. So that's there's only one graph here. So it should be decreased to V naught over 9, answer 1. Right? Now, even though a graph is asked, without doing this calculation, you can't get any idea about that value of the terminal velocity. When that is known only, you can select the correct graph. That's a good one. That's a good one. Right? 25. When wind blows over the surface of a still lake, a bunch of water hyacinth floating on water as shown in the figure is observed to move in the direction of wind with velocity v. Consider the following statements made about v. Right, consider the following statements made about v. Magnitude of v depends on the rate at which the momentum is transferred from air molecules to the bunch. Yeah, because now velocity is acquired using an impulsive force and a momentum change. So that is v equals mv minus u over t. This is how the velocity is acquired. Magnitude of v depends on the rate at which the momentum is transferred. Yes, right? Because of the momentum, because of delta mv, this is delta mv, no? Right? So that changes. It's correct. Magnitude of v depends on viscosity of water. Yeah, definitely. Viscous force depends on viscosity. Magnitude of V depends on mass of bunch. Yes, because mass is here. See, mass is a variable. Yes, then all. Right. 26. Two narrow tubes of equal lengths but different radii of cross section are connected end to end, and water is allowed to flow through it as shown in the figure. Right? If V1 and V2 are the average velocities with which water flows through cross sections of tubes, and delta P1 and delta P2 are the pressure differences built up across the tubes as shown, then the ratio delta P1 to delta P2 is equal to. Right? It says pressure differences are same, right? Equal lengths but different radii. Okay. Then we know, since there is a series combination, V over T's are equal. No? Since there is a series combination, V over T1 equals V over T2. Right? We can also expand V over T as AV. Then you can write this as A1 V1 equals A2 V2. Same thing. A1 V1 equals A2 V2. If you expand volume, then AV equation comes. Right? Now, if I apply this here for the first one, let's consider they are radii as R1 and R2. Right? Then A1 is phi R1 squared V1. A2 is phi R2 squared V2. No? 5 to 5 cancels. Now we have something here. So let's subject this and keep it there. R2 squared do R1 squared. Is V1 no V2 no? Right. So let's keep it as 1. Now we can apply our viscosity equation, Poisson's equation. Right? Apply Poisson's equation. Right. Then since V over T's are same, we can at once equate them. No? V over T equals V over T. V over T's are equal now. V over T1 equals V over T2. V over T's are equal. Then this is phi delta V R1 to the power 4 over 8 theta L. And on the other side, phi is delta P1, and phi delta P2 R2 to the power 4 over 8 theta L. Same length, no? Right? Same length. Same length. Then these terms are going to cancel. Phi to phi, 8 theta L to 8 theta L. Right? I need delta P1 or delta P2. Delta P1 or delta P2. Right. See what's happening. Right. Delta P1 or delta P2. Delta P1 or delta P2. If it is subjected, delta P1 or delta P2, if there is subjected, it's R2 to the power 4 over R1 to the power 4. No? We can write the same thing as R2 squared over R1 squared, whole thing squared. No? Use indices. Now for this thing, I have an answer here. R2 squared over R1 squared is V1 over V2. Then this should be V1 over V2 whole thing squared. V1 over V2 whole thing squared. Right? Kind of a tricky calculation. Right? Kind of a tricky one, a tricky calculation. 27. If the coefficient of viscosity of all fluids is reduced below the existing value without reaching the conditions for turbulence, which of the following is not true? Right? If viscosity reduces, which means if this is about if eta reduces. Right, first one, liquid flow rated in narrow tubes will be higher. No, because according to Poisson's equation, right, I'm checking first one, V over T equals phi delta P R to the power 8 theta L. No? Then see what is happening when eta decreases. When eta decreases, V over T increases. Right? When eta decreases, V over T increases. So that is correct. Heart may have to do less work to pump blood. Heart may have to do less work. We can check it out using pressure here. We know from the same equation, delta P is proportional to eta, no? When eta reduces, delta V reduces. When the pressure is less work. It's correct. When the pressure is less, it's a less work. When the pressure is less, it's a less work. So it's correct. Then sucking cool drinks using straw is easier, yes. Because when eta decreases, thickness decreases. Right? When that thickness decreases, sucking is easier. Right? Common sense. Resistance due to air drag in moving cars will decrease. Correct. Because that is given by 6 phi eta RV, right? Or any other viscosity equation. Yes. Always viscosity means that's the coefficient we have to determine the thickness of the liquid. To determine the thickness, right? Last one, terminal speeds acquired by raindrops will become smaller. No, because we have proved an equation for terminal velocity. That is 2r squared g rho object minus rho liquid over 9 eta. When eta reduces, V increases. V increases, becomes smaller, that's wrong. Then it should be 5. Should be answer 5. Right? 28. A river flows steadily at a constant velocity V. At a constant velocity V, a rectangular block of wood having density less than that of what is first held above the surface of water, so that it is stationed with respect to the river bank, and then slowly lowered to the water until the floating condition is achieved and then released, as shown in the figure. Assume that the initial speed of wooden block in the direction of V is 0. Initial speed is 0. Right. During the subsequent motion of the block, which of the following is true or magnitudes, 4 magnitudes of the impulsive force acting on the block? Okay. The viscous force acting on the block and the momentum of the block. Right. Impulsive force. Right. Listen. Impulsive force is given by this equation. Let me mention the equation somewhere. Impulsive force is given by delta mv over t. This is the equation of impulsive force. Now, initially, difference in velocity is very high. Initial difference is high because river flows with v and initial speed of the box is 0. But then gradually it's gaining the velocity. When it is gaining a velocity, difference becomes smaller. When it is gaining a velocity, difference becomes smaller. Then over time, delta V decreases. When delta V decreases, F decreases. It should be a decreasing impulsive force. We have 1 here, 3 here, and 5. Right? Then about the viscous force. Right? Viscous force is always when the liquid slides. When the liquid layer slides. Right? Now, when it is gaining the velocity, liquid layer slides. Then what happens is viscous forces are there. But once this box has obtained the same velocity as the river, both are moving simultaneously. No? Both are moving simultaneously. When both are moving simultaneously, there's no slipping due to liquid surface, slipping due to water surface, which means viscous force should be 0 at the end. Right? If there's no difference in velocity, because it is coming from Newton's equation, F equals eta A delta V over D. When there is no velocity, this becomes 0. When there's no difference in velocity, this becomes 0. When delta V becomes 0, then decreasing to 0. That is only in 5. So let's check out the last one. Momentum increases and becomes constant. Correct. Why? Because initially it has no momentum because no velocity. But over time, velocity increases. When velocity increases, mv increases. And finally, since v is constant, momentum becomes constant. So answer 5. Right? Kind of a combined question with mechanics, impulsive force, and momentum. Right? 29. A thin flat plate ZD is placed midway between two large horizontal plates X and Y, and the space is filled with the viscous oil as shown in the figure. Now consider the situation that the plate ZD is pulled horizontally to the right with constant speed, and plate Y is pulled horizontally to the left with constant speed V over 2. This is pulled to this side with V over 2 while keeping x horizontally. Sorry, x stationary. Then there's no velocity for x. And what's the velocity of z? With a constant speed. Okay, value v is not given. And plate y is pulled horizontally with. Okay, right. So let's say this is pulled to this direction like this with v, something like this with v. Right. So we know the first liquid layer has a same velocity of the immediate contact, right? Then this layer has first layer has the same v to the right. First layer has the same v to the right, like this, right? And about y also same thing applies. Same thing applies. Then this first layer also has the velocity to the left. Then when there are right and left, velocities, there should be one point in between somewhere where it becomes zero. No? When there's a velocity to the left here and the right here, there should be somewhere in the middle, it becomes zero. Should be somewhere in the middle, it becomes zero, right? And this is only V over 2, no? Then it's 5. It's 5. You can't say it's exactly like the middle, and 4 is anyway wrong because this velocity is wrong, right? So there's only one choice. It's 5. It's 5. Always adjacent layers has the same speed. Adjacent layers of liquid has the same speed of that immediate contact, right? That immediate contact. A small logic. 30. The gap of 2 centimeters between two horizontal plates of surface area 500. This should be square centimeters, not cubic centimeters. Square centimeters is filled with an oil having the coefficient of viscosity 0.2, something like this. The gap is 2 centimeters. This is filled with an oil. This is filled with an oil. Filled with an oil. Right? Coefficient of viscosity 0.2. Right? And area of plate is 500. Area of plate is 500 square centimeters. A horizontal force 5 newtons is applied to the upper plate while keeping the lower plate at rest. Okay, for this one, 5 newtons applied. What is the velocity of the middle layer of foil if the velocities of foil layers vary linearly across the gap between plates? Okay, if I find the velocity of the plate, then middle layer has the average value, no? Because if it is from V to 0, right, it will be the average. So let's find out this V. Apply Newton's equation. F equals eta A delta V over D, right? Then F is given 5. Eta was 0.2. Area is 500 10 to the power minus 4, right? V minus 0 is V. This is V minus 0, no? It's V. And D is 2. 2 times 10 to the power minus 2. Simplify and see. Simplify and see. Okay. What is cancelling here? See, 10 to the power minus 2 to. This is also 10 to the power minus 2, no? Everything cancels. Then this is 5 to 5. 5 to 5 cancels. Then this is 0.2 times 10, which means V equals 10. V equals 10 ms minus 1. But this is the velocity at here. This is the velocity at here, V. Right? Velocity here is 0. Right? Then in the middle it should be V plus 0 over 2 average value. Right? Then 10 plus 0 over 2, that is 5 ms minus 1. That is 5 ms minus 1, the average value. Right? (31) A parachutist bails out from a helicopter at time r equals 0. After a certain time, he opens his parachute and then reaches the ground. Which of the following graph best represents the variation of the vertical component of velocity v of the parachutist with time r? With time, it should be t. with time t. Should be time t. Right? The idea here is coming from the variation we draw about an object which falls under a viscous fluid. Right? VT variation, we have read this in the theory. Right? This is the VT variation of an object which falls under the raging terminal velocity, which falls under viscous force in a viscous medium, right? So always it is moving, it is traveling with a decreasing acceleration. It travels with a decreasing, right? With a decreasing acceleration. Decreasing acceleration is not a deceleration, that is a decreasing acceleration. The only decreasing acceleration here given now, right? There are two accelerations given, decreasing ones. One is given, 5 is given. Those are the decreasing accelerations. And hereafter, when the parachute is open, another small part to be argued. When the parachute is open, his velocity becomes smaller. When the parachute is open, right? Then his velocity should reduce until he is reaching a terminal velocity again. Right? Always when terminal velocity is reached, acceleration should be zero at the end point. Acceleration should be zero at the end point. Now in this case, acceleration is not zero at this point because there is a non-zero gradient. But here it is becoming zero. So final answer is answer 5. Final answer is answer 5. I draw some kind of like similar type of variations in the class also. Right? 31. Right? Then 32. A small spherical liquid drop of radius r and density rho falls with terminal velocity v in still air. The coefficient of viscosity of air is eta and the density of air can be neglected. Density of air can be neglected. Consider the following statements regarding the terminal velocity v of the droplet. Right. So we have a proved equation for terminal velocity. Use that. V equals 2r squared g rho object minus rho liquid over 9 eta. Right. Now it says density of air can be neglected, which means we can neglect this. We can consider this as 0. Then what's remaining is 2r squared g rho, right? Rho is given as rho, no? That was it, yeah. Rho object is given as rho over 9 eta. Check these statements now based on this. Check these statements now. It is directly proportional to r squared, correct? Right? V and r squared directly proportional. It is directly proportional to rho. Yes, it's also correct, no? It is directly proportional to rho. Inversely proportional to eta. Yeah, that is also correct, no? Then all ABC are true. All ABC are true. Right? All ABC are true. All ABC. Right? That's a simple one. As long as you know the proved equation for terminal velocity of a sphere, simple, nothing to do. Right? You have to know the equation. You have to know the equation. Right? Next. 33. It's the last one. A car has a grease nipple of length 3 times 10 to the minus 3 meters and a diameter 5 times 10 to the minus 4. If diameter is given, we know radius should be 2.5 times 10 to the minus 4 meters radius. Right? If the coefficient of viscosity of grease is 80 Pascal seconds, what's the pressure difference needed to force a volume of 10 to the minus 6 cubic meters of grease through the nipple in 10 seconds? Take fourth power of 2.5 as 40 and 5 equals 3. Right. So apply. We have only one option, Poisson's equation. Right. Apply Poisson's equation. VOT equals 5 delta P r to the power 4 over 8 theta L. Right. V is given 10 to the minus 3 minus 6 over time is 10 seconds. 10 seconds. Right. Pi is 3. Right. We need to find delta P r to the power 4. Right. R here is 2.5 times 10 to the minus 4. No? Then complete power 4. Complete power 4 over 8 eta. Eta, what was the value? Eta 80 L 3 times 10 to the minus 3. Right? And this value is given. See? Now, shall we cancel this 10 first? This 10 to this 80. This 10 cancels. Okay, then here 10 to the power minus 6 remains. 3 times delta P. And from here, 2.5 power 4 comes. That is given 40. 2.5 to the power 4. It is given as 40. 10 to the power minus 4 to the power 4 is 10 to the power minus 16. Whole thing over. This is 8 times 8. Right? Times 3 times 10 to the power minus 3. Simplify. Simplify. Then 3 to 3 cancels. This is 8 times 5, no? 8 times 5. Right. Then the rest is 10 to the power. 10 to the power minus 6 to 16 cancels. Then minus 10 remains. Minus 10 remains. Then minus 3 and minus 10 cancels. Minus 7 remains. Subject delta P. Delta P equals, right, 8 over 5 times 10 to the power 7. 8 over 5 times 10 to the power 7. It's right. 8 over 5 times 10 to the power 7. 8 over 5 is 1.6. 8 over 5 is 1.6. 80 over 5 is 16. No? So 8 over 5 is 1.6. 1.6 times 10 to the power 7. This is in pascals now. 1.6 times 10 to the power 7. Right? Fifth one. A small calculation again. Not a big deal. A small calculation again. Right? Okay, feel free to ask if any questions. Right? We have discussed around 18 means around like 17 questions today also. In last day also I discussed around 17-18 questions. Right, so altogether from viscosity, all the past papers are covered now. All the past papers are covered now. Around 33 questions are covered now. As past papers, all other new questions and model questions I have done in the class and in the theory class, and I'll be putting the rest of the questions in papers. Right, so I'll be putting the rest of the questions in papers. Right. Okay then. Any questions? Any questions? All good? Right. Okay then. So we have come to the end of the questions I planned for today as well. And in next S2A discussion, probably I'll be taking something from elasticity, thermal, or maybe rotational motion, something like that. You can get all the updates through the channels, right? Through all channels, you can get updates through all the channels, right? Okay then. Then if no questions, we can wind up, right? We are just 20 weeks ahead of the exam. 20 weeks, just 20 weeks, right? So don't waste time and stay safe during this crisis situation, and optimize and utilize your time to the fullest, being inside your house, your home, unless that's somewhere essential to go. If you have a class or going to a school or something like that, that's fine, you can go. But try to stay inside homes as much as possible, because some kind of a crisis situation is happening around the country, right? Okay then. So if no questions, we'll wind up, right? And see you again in the next SVA discussion or in the next class, right? Okay then. Good night and goodbye. See you.